Number one, we have the limit as x tends to infinity of 5x plus e to the negative x, and that's all over 7x. I'm going to rewrite this as 5x plus 1 over e to the x, and that's divided by x. The reason I'm doing this is because I want to really think about what this term is doing. X is getting larger without bound. So as x gets larger, e to the x is also going to get larger. So in this fraction, the numerator stays at 1, but the denominator is getting larger without bound. It's tending to infinity. So this is going to 0. Now this term is tending to infinity, and this term is tending to infinity. So we've got the form infinity over infinity. That's going to allow us to use L'Hopital's rule, which I'm indicating here with that L. Now I'm going to return to this form because that's going to be easier to differentiate. So if we differentiate the numerator and the denominator using L'Hopital's rule, we will get 5 plus, actually be minus e to the negative x. The derivative here would be e to the negative x times the derivative of the exponent, which is negative 1. That's why that plus turns into a minus. And then that's going to be 7. Well, as we said before, this part is tending to 0. So I think we can just go ahead and say that's going to be 5 over 7. In number 2, we are asked to find the limit as x tends to 0 of 5 sine x plus 2 cosine x plus x, all divided by 7 cosine x plus x squared. So we need to check to make sure that this belongs to one of the indeterminate forms, either 0 over 0 or infinity over infinity. So we'll substitute in 0, and let's see, if we do that, we get 5 sine 0 plus 2 cosine 0 plus 0, and that's all over 7 times cosine 0 plus 0 squared. The sine of 0 is 0, but the cosine of 0 is 1. So I think this is going to be 5 times 0 is 0, 2 times 1 is 2 plus 0, 7 times 1 is 7, and then plus 0. It looks like it's going to be 2 over 7. In number 3, we are asked to find the limit as x tends to 0 of 1 minus cosine of 2x plus 3 sine x minus 3x, all divided by e to the x minus 1. So the first thing we should do is substitute the 0 in and see what happens. If we substitute in 0, we're going to get 1 minus the cosine of 0. Well, that's 1 minus 1. 3 times the sine of 0. The sine of 0 is 0. I believe that turns out to be the numerator is 0. E to the 0 is 1, so we're going to get 1 minus 0 minus 1. That's 0. So it is 0 over 0. So that means we may apply L'Hopital's rule. We are allowed to apply L'Hopital's rule. So we differentiate the numerator and the denominator and hope we get something good. Well, let's see. The derivative of 1 is 0. The derivative of cosine is negative sine, but there's that negative right there. That'll be positive sine of 2x multiplied by the derivative of the inside function, and that's 2, right? We've got a chain rule situation. Plus 3 times cosine x minus 3. In the denominator, the derivative of e to the x is e to the x. The derivative of x is 1, and the derivative of 1 is 0. Now what happens? Well, we substitute in 0 again. The sine of 0 is 0 and the cosine of 0 is 1. So we're going to get 0 plus 3 minus 3 is 0. And we're going to get 1 minus 1 down here. We're getting 0 over 0 again. So that means we can apply L'Hopital's rule one more time. And maybe we'll get something we can use this time. So the derivative of 2 sine 2x is going to be, well, let's see, that 2 will come along, and we've got the cosine of 2x, and then multiply by the derivative of the inside function. So there's a 2 there. Minus 3 times the sine of x. And then down here we're going to get e to the x minus 0. I don't think we're going to get 0 over 0 this time. Let's e to the x. Alright, so cosine of 0 is 1. So this will be 2 times 1 times 2 is 4 minus 0, because the sine of 0 is 0. And we're going to get e to the x, e to the 0 is 1. It looks like it's going to be 4. In number 8, we have the limit as x tends to 0 from the right of x to the x. So that's going to be of the form 0 to the 0. That is an indeterminate form. So, in the case we've got an indeterminate form like 0 to the 0, we've got something raised to a power. What you want to do is take the natural log of the function. So we're going to take the natural log of x to the x. And then using the rules of exponents, we can rewrite that as x times the natural log of x. And now we'll just find the limit of this expression. Well, as x tends to 0, that's tending to 0. You might remember that this limit, the limit of natural log of x as x tends to 0 from the right, that's negative infinity. That's also an indeterminate form. Here's what we can do. We can rewrite this as the limit as x tends to 0 from the right of the natural log of x over 1 divided by x. I think you can convince yourself that this is equivalent to what we have over here by remembering how you divide by fractions. To divide the natural logarithm by 1 over x, you multiply natural log of x by the reciprocal of 1 over x, which would be just x. So this would be natural log of x times x. They are equal. Now, this is tending to negative infinity, and this is tending to positive infinity. Don't worry about the different signs. It's still the form infinity over infinity. We can use L'Hopital's rule. The derivative of the natural logarithm of x is 1 over x. Now what about the derivative of 1 over x? Well, remember that 1 over x can be rewritten as x to the negative 1. So when you differentiate, you're going to get negative 1 x to the negative 2, which is negative 1 over x squared. So you're dividing fractions again. I'm going to rewrite that as 1 over x times the reciprocal here, and that would be negative x squared over 1. I think that's just negative x. And now the limit as x goes to 0 from the right of negative x is going to be just 0. However, that's not the answer. We are not finished. Remember that we took the natural logarithm of our original function. So what we calculated is not this limit. We have to pay for finding the natural log of this function. So we need to undo the natural log. And we do that by using e. The answer is going to be e to that power, e to the 0, is 1. And that's the correct answer.